Thank you so much for the introduction. So today in this, I want to present a paper that provides a series of improvements on a specific preimage sampler using Lattice Gadgets. And along with some further optimization, we use it to obtain a signature scheme, which we called Phoenix, which combines some of the nice features from both Lattice signature paradigms. But first, to put this into perspective, we have two main signature paradigms right now, which are hash and sign and fiat chain with aborts. And we have a representative for each one, which have been chosen for standardization by NIST, namely Falcon and Dilithium. And they're kind of on both ends of the spectrum between size and scheme complexity, in the sense that Falcon has very small sizes, but is also a fairly complex scheme, while on the opposite, Dilithium is much simpler, but also has slightly larger sizes. There have been proposals of improvements of these two schemes, which are under evaluation, with Salmae, which is a simpler version of Falcon with similar sizes, and Hite, which increases the scheme complexity of Dilithium, but also reduces significantly its size. And on another level, we have two schemes, two hash and sign schemes, Robin and Eagle, which appeared at Crypto last year using Lattice Gadgets to kind of rehabilitate this approach as well to design hash and sign signatures. But there still seemed to be a fair distinction between fiat chain with abort schemes and hash and sign ones. And this is where Phoenix comes into the picture by having a hash and sign scheme that draws some of the nice benefits of both signature paradigms, in the sense that it's a much simpler scheme than previous hash and sign signatures. It also can be instantiated with a wide variety of distributions. And it also inherits from the benefits of hash and signs, which is to have, for example, a tight quorum security. But before we get into more details about Phoenix, let me remind a few preliminary notions that we'll need. The main security assumption that underlies mostly the forgery of all hash and sign scheme is the ISIS assumption for inhomogeneous short integer solution. And it can be stated as follows. I give you a uniform matrix A and a uniform vector U mod Q, and I tell you that it's hard to find a short vector X that verifies AX equals U mod Q. Well, it is hard unless you know a secret information known as trapdoor on the matrix A, which allows you to solve the problem. It means that you can invert the function that maps X to AX mod Q over a bounded domain, meaning over short vectors X. But more than that, it gives you the ability to randomize this preimage finding method without leaking your secret knowledge of R. And this is called preimage sampling. Now, based on a preimage sampling procedure, you can directly design secure hash and sign signatures following the Gentry, Pykun, and Vicuthanathan framework, which essentially says that you hash the message to get a target U, and then you use your trapdoor sampler to provide a short signature X. But there are several choices for these trapdoors and how to construct those samplers, and the ones that I want to focus on today are gadget-based samplers, which I'm going to remind right now. So let's first go to the first part of our contribution, which is on the sampling part, and we'll see the signature part later on. So in 2012, Mitchenschel and Piker defined a family of matrices, A bar, which are of the following form. So you have a first block, which is a matrix A, which can even be further decomposed as the identity matrix and a matrix A prime. And the second block is some G minus A times R. R is our trapdoor matrix composed of short elements, and a product A times R can actually be made public under the harness of ISIS and also decision ISIS. And the key component here is this G matrix, which is called the gadget. It's a public matrix, which should allow for an efficient short inversion, meaning that ISIS on the matrix G should be fairly simple. So how do we produce preimages for matrices of this form? We first compute a short Z that verifies Gz equals U using the efficient short inversion. We return R prime Z as the preimage of U. It's that simple. The problem, though, is that if we do so, even when using an instantiation of gadgets, which is the base B recomposition matrix, well, collecting many preimages will leak some information on our secret trapdoor, which we don't want for security. So to bypass this problem, we perturb those preimages and add a mask to obtain P plus R prime Z, and we also update the gadget inversion to keep the correct equation. So we invert U minus A bar P instead of just U. The question now is, how do we choose this mask? What conditions does it need to satisfy? Well, the first method is called the convolution method from the original paper of Mitchell and Pikert. And the idea is that if I sample a Gaussian element Z on the gadget coset so that it verifies G is equals U, then R prime Z will follow again as a Gaussian distribution, but whose covariance depend on R. And this is why we have a problem if we just send R prime Z, because I can mount statistical attacks to recover R. So to avoid that, I will sample P from another Gaussian distribution whose covariance will cancel out this dependency so that I end up with something that has a width that no longer depends on R. This approach has the benefit of being rather compact, but it's also fairly complex in the sense that you need all of these complex Gaussian sampling for sampling Z on a gadget coset and sampling P from a highly skewed distribution. The second approach that I want to present is using rejection sampling. And for that, we need to understand better what to hide exactly. We want to hide R, but R appears as RZ in the top component, which is the shift we want to hide. And unfortunately, Z also appears in the bottom component, which leaks some information on this shift. And this is why in the convolution method, you cannot set P2 equals to 0 as is, because it will leak some information leading to the same statistical attacks. But what if we really want to set P2 equals to 0? Well, in that case, we can draw a little bit of a parallel with Fiat-Shamir identification schemes. In those schemes, we prove knowledge of a secret S by first committing to a mask vector, sending A times Y. We get back a challenge C, and we respond with Y plus SC. Well, if we take our situation where P2 equals to 0, we have a similar problem in the sense that we can see the commitment as just being AP1, the challenge would be Z, and the response would be P1 plus RZ. But again, as I mentioned, it leaks some information on the secret. So the simple countermeasure that was used for Fiat-Shamir identification scheme is to use rejection sampling. And we can use the same countermeasure to have a secure sampler using this method. And this is what Lubashevsky and Wicks came up with in 2015, which is to set P2 equals to 0, set Z to be the gadget inversion of U minus AP1, and then reject every time there is a statistical leakage. And you start over until you have until you accept. This approach is much more versatile than the convolution method because it does not need to rely on specific distributions like Gaussians, and it can be instantiated with uniform distribution, for example, but although plenty of other choices. The slight caveat, though, is that if you set Z that way, it's likely going to depend on P1, which we don't want for security as it will thwart the whole security argument based on rejection sampling. So to smooth out this dependency, we require that U minus AP1 should be statistically uniform. And in their paper, they see U as an arbitrary target, which means you cannot assume anything about it, in which case the statistical regularity of U minus AP1 falls onto AP1, which unfortunately drastically impacts performances negatively. The reason for that is that having AP1 statistically uniform requires a high entropy for P1, which can be achieved in two ways, either by having a high dimensional vector with a low variance or a low dimensional vector with a high variance. But either way, you have larger parameters and as such, larger preimages, larger signatures, and so on. And our observation is that in some contexts, we can assume something about the syndrome to avoid the regularity argument from LW15. And in particular, for example, in the context of hash and sign signatures, where U is the hash of the message, we can salvage some of the entropy to require U minus AP1 being uniform without having P1 to have a high entropy. And as such, we can have a low dimensional vector with a low variance all at the same time, which compacts parameters, compacts the preimage, compacts the signature. So this is what the sampler looks like. And for those of you who are familiar with it, it's the same as from 2015, but we have parameter conditions that make it more efficient. So you sample P1 from a source distribution, you invert U minus AP1 to get V2, you construct P1 plus RV2, and you reject when there's some leakage, and otherwise you output V, which satisfies the correct equation. Okay, so it's fairly nice. We managed to optimize a little bit the sampler, but can we go even further? Well, In the case of non-arbitrary syndrome, we can actually try to combine this rejection sampler to the approximate trapdoor approach from Chen, Genizé, Mukherjee. The idea is that instead of finding a short v such that a bar v equals u, it's sufficient to find a short v prime such that a bar v prime equals u up to a small error e. And as long as this error is small enough, then it preserves the security for a smaller signature v prime. And in the context of Mitchenson-Piker trapdoors with the gadget of the base B recomposition, their idea was to use only the high order decomposition to get V prime, and the low order components are going to define our error, which should stay small. So this is our rejection sampler, and we change it into what we call the approximate rejection sampler in the following way. So we, instead of taking the full base B decomposition, we take only the high order components, and the low order components are going to define our error E. Now, because A bar has the identity in the first block, we can actually directly merge this error E to the first part of V1 so that we end up with a vector V that still satisfies the exact equation, but with a slightly larger V1. The question now is, how larger is it? Well, in our case, the preimage error can be bounded by B to the L minus 1 and is roughly uniform. And in particular, it is much smaller than in the original paper of CGM19, which relied on the convolution method and as such Gaussian distribution, which were a little bit larger. And in turn, it allows us for dropping more entries of the gadget for the same security. And we can even go up to a square gadget by choosing L equals K minus 1, which matches the behavior of the semi-random sampler, which were introduced last year for Robin and Eagle. Nevertheless, our error is still a little bit slightly larger than with the semi-random sampler, but we have a much smaller V2. And this is also going to be a key component in the design of the signature scheme. So this is it for the sampling part. So we managed to optimize the signature size, but also the public key size because we reduced the number of dimensions in the gadget, so in the matrix A bar in the same time. Now let's see how to obtain a decent signature scheme from it. For that, I will first do a quick overview of the different methods and their advantages and drawbacks. We have two main families of hash and sign signatures, which are either following and true trapdoors like Mitaka, Salmae, and Falcon, or gadget-based trapdoors with either convolution sampler or the semi-random sampler, because the rejection sampler is not efficient. And the advantage of true trapdoors is that they give very good performances, but they're also fairly complex to design the scheme and to implement. And this approach was tried to be made simpler using the convolution sampler or the semi-random sampler to have a slightly simpler scheme, but it still relies on convolution of Gaussians. But it made the scheme less efficient, even when using the I and true assumption, which is here to kind of match the performance of N true. And the common thing also about all of the schemes that I mentioned is that they all need to rely on Gaussian distributions, which might not be preferred in a variety of contexts. And the only sampler that seems to be discarding this constraint is the rejection sampler, but it's not efficient. And this is where Phoenix goes, is that it takes the same benefits as the rejection sampler, and it's also much simpler because it does not need to rely on complex Gaussian sampling, but we still have a rejection step. But it also makes the scheme more efficient. Okay, so how do we design Phoenix from this? Well, we just have our Mitchenson-Piker trapdoors, we have our approximate rejection sampler, and we plug that directly into the GPV framework. And we end up with a signature scheme, which is called Flamingo. The reason why it's not Phoenix yet is because, yes, it has short-ish signatures, but it also has fairly large public keys. So can we reduce the public key size to have a more decent signature scheme? Well, the answer is yes, by using a similar idea to the approximate trapdoor setting, by splitting the public key matrix B into the low order bits BL and the high order bits BH. And we now want to rewrite this verification equation to be only a function of BH so that we don't need to transmit BL to the verifiers, thus compressing the public key. So we split B that way. We rewrite this equation, making this BLV2 term appear, which is a short compression error. The reason it is short is because BL is some lower of it, so it's short by nature. And V2 is particularly short because of our approximate rejection sampler. Recall that V2 is some high order base B decomposition of something, so its coefficients are bounded by B minus 1. And in our paper, we also showed that the optimal base in this case is B equals 2, which means that V2 is ternary, which makes this compression error very small. Now we can merge directly in the sampling procedure this compression error to the first part of V1, just like we did for the sampling error. And now we need to have a little discussion on how much bits we can cut. Well, if you choose L prime to have a compression error that stays below the sampling error, then you don't increase this first part by much. And so you preserve the norm roughly the same, and you thus preserve security. And in our case, we can essentially drop half of the public key while staying below the sampling error, which means our compression comes almost for free. And this is due to the fact that V2 is particularly short. In particular, our key compression is much simpler than with Fiat-Shamir identification schemes and Fiat-Shamir with abort signatures because it does not need to rely on extra hints or rejection sampling for correctness or security. And this is what we end up with. This is Phoenix, which is Flamingo with key compression. So in terms of concrete sizes, this is what we get for NIS2, NIS3, and NIS5 levels. I put the lithium here just as a frame of reference, but it's not really comparable as it's not a hash and sign scheme. The closest hash and sign scheme in essence is Eagle, which is also based on gadgets, it's also based on gadgets on the LWE assumption, just like Phoenix. So we can see that we end up with slightly smaller signatures, but also we gain about 25% on the public keys, which is also fairly nice. And this is it for my talk. So to wrap things up really quickly, what we wanted to achieve in this paper beyond the sole signature application was to really rehabilitate this rejection sampler as it has some nice features that could benefit from other applications. And we managed to optimize it in specific contexts when the targets are uniform, along with some further optimization with approximate trapdoors, which led to this signature application with also a fairly nice way of performing key compression. And it also shows that Fiat-Shamir schemes and hash and signs one are not so far apart, which I think is theoretically interesting. Because we end up with a scheme that has the same features as Fiat-Shamir schemes in the sense that it can be instantiated with many distributions, it's fairly simple, and it also inherits from this hash and sign paradigm by having this tight quorum security, for example. And just to conclude, as far as future work goes, I think the next step will be to identify distributions that keep the same level of compactness or are even more compact, but by having an easier to protect rejection step, which is the next step towards concrete implementation security. And also, I would be interested to see other application of the approximate rejection sampler, and also to see if we can optimize it further using the I and true assumption, which seem to make things more compact for other methods. And this is it for my talk. Thank you for your attention, and feel free to ask questions.
Thank you very much. Are there any questions or comments?
Very nice talk. Thank you. So on the last bullet that you showed, you mentioned the inhomogeneous and true. So would that be like an adaptation of Robin in your framework?
So I haven't yet looked too much into it, but yeah, that would be to have a version of Robin based on this rejection sampling approach. Because of the form of this second block, here we can do this G minus A times R and have rejection fairly simply. But with I and true, it's a little bit more complicated. So it's not that straightforward to me. This is why it requires a little bit more work. But my hope is that it can make things more compact because the second block would be slightly smaller.
So why is it inhomogeneous and true rather than like just the simple and true assumption?
It's a good observation. I think we are still in the realm of gadget-based samplers, which the untrue is designed for. The untrue assumption is designed for. Based on untrue solely, I think we just fall back on some signature scheme like Falcon or something, which I don't think is really relevant with rejection sampling approach. Yeah.
Thank you.
I mean, it won't, the rejection sampling approach, even if it works for the untrue assumption, I don't think it's going to make things smaller than Falcon.
Any other thoughts, questions? Well, thank you very much again.
Thank you.